Yeah, so.
Okay, yeah, so yeah, Wenhua Zhao is, because obviously Thobani presented in the morning, so thanks Wenhua for jumping in. And Wenhua is going to talk on reduced group velocity in water wave and structure interaction. So Wenhua, the floor and time is yours.
Yeah, thanks for the introduction, Amin, and yeah, full screen the slides. So we got someone can't make this presentation, so I just make some slides during the meeting, and hopefully that's clear. Excuse me. And so the topic I would like to share today is the reduced group velocity for water waves due to wave stress. And to give you a flavor of what I'm going to talk about, so I'm going to start with this video. So this is like two vessels moored together in a side-by-side configuration. And what you can see here is the very strong resonant waves inside the two vessels. And yeah, so it's the video a little bit not as smooth as it used to be. It's supposed to be, but that's like waves propagate along the gap between the two vessels. And to look at the wave propagation along the gap, we conduct some experiments, and we simplify the problem, and we simplify the vessels to two rectangular boxes and elongate boxes. And as you can see here, we have like two vessels moored together, and they are identical vessels. And at full scale, it corresponding to 200 meters long vessel and 11 meters draft, and also the gap width between the two vessels is 4 meters. And we do the testing in the wave basin at Shanghai Jiao Tong University, as shown in this snapshot. And this basin is 50 meters long, 40 meters wide, and the water depth was 10 meters. So as you can see here, the vessel model is 3.3 meters long, sitting in the center of the wave basin. It's yeah, quite a small model compared to the huge wave basin. And what we do in the testing, so we first we look at some linear excitation of the gap resonance, and on the left top left corner, that is a wave transient wave group. We use this to pass to excite the gap resonance, and these waves pass through the two vessels from left-hand side to the right-hand side, and we have wave gauge centered in the center of the gap, and we measure the surface elevation, which is shown on the bottom right corner. That is the red curve is a response. So what you can see here is the incident wave is quite a clean signal, which is a focused wave group. And when it passed through the gap, due to the wave structure interactions, and the wave surface elevation got quite complicated, like shown on the right, on the bottom right corner. And this is not surprising, because we got the incident wave frequency lined up with the resonant frequency of the waves inside of the gap. So to give you a clear idea, I plot them on the top right corner. That is the response power spectrum, the power spectrum of the incident wave, which was the black curve, and then the blue curve with quite a few spikes. That is the response corresponding to the red curve. Sorry, that's not inconsistent here, but that's one is the incident wave energy, the other is the response measured inside of the gap. You can see they lined up quite well in frequency. That's why we get very strong resonance. And as you might ask, why there are so many spikes in the response on the top right corner, that is because we excite the various resonance mode inside of the gap. If you look at the middle, the grain curve, which is a half sine wave, that is one of the resonant mode inside of the gap. And then the solid blue, solid red curve, which is 3 half wavelengths. That is another vibration mode inside of the gap, or the surface elevation mode. And each one is kind of integral half sine waves, because here this is like a beam-C excitation. That's a symmetric excitation. So we got the odd mode, which is the symmetric mode with respect to the center of the gap. So the question is, what if we have a nonlinear excitation, for example, the picture here, and I highlight the gap resonance mode, for example, the first gap resonance mode with the dashed line, and corresponding to the fourth scale, that's 7 seconds at fourth scale. And what if I have a 14 seconds wave, for example, swells from southwestern ocean, approach the two side-by-side vessels. By linear theory, we're gonna get nothing there, but due to the nonlinear excitations, we get something. And before I show you the results, I would like to show you this slide. This is a very simple Stokes type wave demonstration, and this is like showing the second order nonlinearity of the waves, and then we can do the phase decomposition, which is like 180-degree difference. If we combine these two waves with 0 degree and 180 degree, we're gonna have the if you add them two together, you can see the linear components gonna be cancelled, and you're gonna have 2 times the second harmonic. And if you use the first one minus the second one, you're gonna have the linear component. So this is the way we separate the different harmonics. So now I'm gonna show you the results. So from the left-hand side, that is the black curve is the incident wave, and the red curve is the power spectrum of the response. You can see we have significant responses at the frequency for the natural for the gap resonance. And if I decomposed the harmonics, and it's shown here. The linear component is the blue curve, and then the red one is the second harmonic. So now you can see the second harmonic is as significant as the linear one. So that's because of the resonant mode inside of the gap. And then that is only one point. In the experiments, I have a series of wave gauge installed inside of the gap, as you can see here in the picture below. And so here we have a series of wave gauge, and at each wave gauge, we can do the analysis for the response curves. And then we separate the linear components on the left-hand side, and then the red curves are the second harmonic, which corresponding to the gap resonance. And from the left-hand side, you can see that that's pretty much from the wave gauge 1 to wave gauge 7, essentially from the top to the end. That's identical waves pass through the gap, because there's no resonance, no interactions with the gap modes. But if you look at the right-hand side, you can see clearly a very clear structure shape, and you got the wave energy enter from the two sides, and they propagate from the two sides to the end to the center of the gap, and then they reflected back to the top, and at the end, some of the wave energy gonna escape. Some of will be reflected back, and as time goes on, it's gonna be decayed totally. So this is for the beam C. More interesting is the head C. So if you look at this one, we have waves excite the gap resonance from one end to the other. From this slide, that's from the top to the bottom. And on the left-hand side, that is the linear component. On the right-hand side, that is the second harmonic. And the second harmonic corresponding to the gap resonance mode, or the wave resonant mode. And on the left-hand side, you can see when the waves propagate from the top to the bottom, it takes only 1 second. If you look at the time axis, the horizontal axis. So this is -1 seconds, and at the bottom, that's 0 seconds. So that's only 1 second. But if you look at the resonant modes from the left-hand side, that is from 0, and to the bottom one, that's 7 seconds. So it takes 7 seconds for the resonant waves propagate from one end to the other. But for linear wave, which is nothing to do with the resonance or off resonance, and it only takes 1 second. So the resonant waves have been significantly slowed down. And to further investigate that, we plot the frequency and also the wave number for that, for the gap resonant mode, and it gives us the opportunity to look at the phase velocity and the group velocity of the gap resonance mode. And here, this is a picture. I should simplify that if I got time. But the dots are the experimental results. That's the gap modes frequency corresponding to the left-hand side vertical axis. And once we know the frequency omega for each mode, and also the wave number for each one, and we calculate the this and the group velocity. And the solid curve here, the solid blue curve is the phase velocity we calculated based on the experiments. And then the solid red curve is the group velocity of the resonant waves inside of the gap based on the experiments. We compare that with Bernard Mollon's theoretical model, and which is the dashed line. You can see they match quite well. And then we also compare to the free waves, and which is the dotted line. And the dotted line, you can see that. And if you compare these curves, in particular the dotted red curve and the dashed or the solid red curve, you can see the wave group velocity inside of the gap has been significantly reduced. And that is something quite interesting. And the reason for that is because of the like the added mass of the resonance. Essentially, the energy exchange between the water inside of the gap and also the water underneath of the vessel. That is the physical explanation for that. And yeah, so if I summarize today's presentation, so I showed some results which is demonstrating the water waves can be excited through a nonlinear process. For example, the frequency doubling process, and due to the like the resonant responses of the water waves inside of the gap, the group velocity associated with the resonance mode does not vary much between the different modes, and this helps the group maintain the like the group structure of the waves, and that's why we can see the very clear group structure propagating from one side to the other side, or from the two ends towards the center, and the other way around. And yeah, the most striking phenomenon is the group velocity associated with the resonant mode is much smaller compared to free waves for deep water in deep water with comparable like wavelengths, and that is the main takeaway from this topic. And if you would like to learn more details, and you can see the reference listed here. And happy to take questions. I hope this is clear. Yeah.
Yeah. Thank you very much, Wenhua. That's excellent. Thank you. Excellent improvisation indeed. All right. Yes, we have time for questions. Okay, so I may start with the first one. So I have a question regarding the laboratory experiments. So you, if you can go back maybe to this slide where you show the initial pulse which has been generated. So you generated a Gaussian wave group, basically, right?
Yes. Yeah.
Okay, so have you varied like the steepness there, especially if you consider the higher harmonics and the response? Have you also changed the steepness of the wave packet to see the influence of the resonant modes?
Yeah, that's a good question. We have doubled the amplitude of the incident wave, and we found the similar like a phenomenon, and also the like the linear components can be scaled from one testing to the other through a a coefficient, and the second harmonic can be scaled from one testing to the other with the same coefficient but squared. So that gives us confidence that this process is like a frequency doubling process, or like second order harmonics. Yeah.
Second, yeah. And have you also tried the case where you have like oblique waves running on the structure?
Yeah, we have the waves from beam side on, and also from head on, which and also from 45 degree in between the two scenarios. And for that one, it's pretty much a superposition of the the beam C and the head on result. So yeah, that's like if I show the beam C and head C, then that one is not quite exciting.
Yeah, that's okay. Yeah, of course. Okay, thank you. Yep. So we have time maybe for another short question. Okay, seems it's not the case. So please join me in thanking Wenhua again for the very nice presentation.
Thanks.
Okay, so next presentation is by Giulio Passerotti. Is he there?
Yes, I'm here.
Excellent. Yeah. So okay, maybe share your screen. Just see if anything works. Yeah, and Giulio is going to talk on interactions between irregular wave fields and IC, a physical model for wave attenuation and ice breakup.